In this video, you're going to learn how to construct the Brillouin zones for any given two-dimensional lattice in 5 simple steps. The two physics concepts we're going to use for this are Wigner-Seitz and the reciprocal space. And that's because, as an analogy, this is not the official definition, but as an analogy, we can imagine Brillouin zones as nested Wigner-Seitz cells in reciprocal space. If you are already familiar with both of those concepts, that's wonderful, because you will probably find this easy, but I'll do my best to explain it in a way that can be understood even if you don't remember how to set up a Wigner-Seitz cell or how to set up the reciprocal space. Usually problems or assignments related to Brillouin zones give you a specific lattice, like for example a square lattice or a rectangular lattice, and then ask you to construct the Brillouin zones for that lattice. So that's going to be the focus of this video. I will first explain the 5-step process, and then we're going to apply it to a specific example so you can see it in action. The 5-step recipe for constructing Brillouin zones is the following. First, we're going to set up the reciprocal lattice of the given lattice. Then, in that reciprocal lattice, we're going to choose a central atom as our origin. Step number 3 is then marking the neighbors of the central atom we have chosen. And not just the nearest neighbors, but also the second nearest, third nearest, and depending on how many Brillouin zones we want to construct, perhaps even the fourth nearest or fifth nearest neighbors. Then, for step number 4, this is where knowing how to construct Wigner-Seitz cells will become really useful. We're going to construct perpendicular bisectors on the vectors connecting the origin we've chosen to the marked neighbors. After step 4, we're going to end up with a grid of lines around the origin, and step 5 is only a matter of definition, because the Brillouin zones are defined in such a way that the nth Brillouin zone is the area that one can reach by crossing n-1 lines, starting from the origin, of course. If that sounds a bit abstract, and to be honest it does, give me a second to visualize it. Let's say this is our origin, and suppose the grid of lines we constructed around it looks somewhat like this. It's not going to look this simple in reality, but the purpose of this drawing is just to hammer home this point. If the nth Brillouin zone is the area we can reach by crossing n-1 lines, that means the first Brillouin zone is the area we can reach by crossing 0 lines, and the second Brillouin zone is the one we can reach by crossing 1 line, and 1 line only. So, if we start walking from the origin and we're not allowed to cross any lines, the only area we can reach is this one. This area right here would be the first Brillouin zone of this imaginary oversimplified lattice. If we start at the origin and walk in all of those directions and we cross 1 line, which is this one, this one, this one, or this one, the only area we can reach is this right here. Because as soon as we cross this line, we would have crossed 2, and that's not part of the second Brillouin zone anymore. So the second Brillouin zone is this green area. But now let's put all of this into practice with a real lattice instead of this oversimplified example. As our example problem, I've chosen the rectangular lattice, because the square lattice is the example in pretty much any textbook that covers Brillouin zones, and in many cases your teacher is not going to put the exact book problem into the exam or into an assignment. If we now recall the 5-step process, step number 1 was to set up the reciprocal lattice. In order to set up the reciprocal lattice, we of course need the basis vectors of the real lattice first, which is in this case very easy, because this is the x direction, this is the y direction. So our a vector simply has length a in x direction. So our a vector is a times the unit vector in x direction. Or if you are more familiar with ijk, it's a times I hat. The b vector has twice the length of that, because b equals 2a. 2a times the unit vector in y direction, aka 2a times j hat. Now for setting up the reciprocal lattice, if this was in 3 dimensions, we would have to deal with all those annoying cross products and stuff, but since we're in 2 dimensions, it's actually pretty simple. To find the respective reciprocal basis vector to any real basis vector, we can simply divide 2 pi by the length of our vector and keep the direction the same. So this would be g1, and for g2, which is going to be the respective reciprocal basis vector for b, we're again going to divide 2 pi by the length of our vector and keep the direction. In this case, we have a factor of 2 in the numerator and in the denominator, so those cancel, and we are left with pi over a times that unit vector. If we look at those for a moment, we can see that this one is twice as long as this one. So our new basis is going to look like this. Now, the x direction is twice as long as the y direction, as opposed to this. If we draw that as an actual grid, we're going to end up with this right here. This is our reciprocal basis vector in x direction, 2 pi over a, and this is our reciprocal basis vector in y direction, pi over a. Now, step 2 is to choose a central atom as our origin. The obvious choice is, of course, the one in the middle, so we're going to mark this as our origin. For step 3, we are now going to mark the neighboring atoms of this origin. The nearest neighboring atoms of this chosen origin are these two, with a distance to the origin of 2 of those paper grid squares. I'm going to mark those in light green, blue for the second nearest neighbors, which are going to be these 4 right here, with a distance of 4 squares each. So let's turn all of those blue. And let me choose brown for the third nearest neighbors, which are going to be these 4 right here, the short diagonal. And just to be safe, let's do the 4th nearest neighbors and 5th nearest neighbors as well. The 4th nearest neighbors are these 4 along this longer diagonal. You can obviously use any colors you want for this, but I do recommend using colors in general because it just makes it easier to grasp what's going on at one glance. And the 5th nearest neighbors are these 2 right here, with a distance of 6 squares each to the origin. So let's start with step 4. And this will seem very familiar if you know how to construct a Wigner-Seitz cell, because we're going to draw perpendicular bisectors on the vectors connecting the origin to all of those marked neighbors, starting with the innermost ones and then working our way out. The vectors connecting the origin to the nearest neighbors are these 2. So if we were to construct perpendicular bisectors on those, they would be here and here. So let's draw those. And then we're going to do the same for the second nearest neighbors. The connecting vectors are those. And the perpendicular bisecting line on, for example, this one, would look like this. So we're going to, again, draw the perpendicular bisectors for all of those, starting with this one, and this one, and this one, which actually crosses the green dots, and this one. Now, the third nearest and 4th nearest neighbors are diagonals, so the bisecting lines will of course be diagonal as well. If we look at this one, for example, the vector connecting it to the origin is this, and the bisecting line perpendicular to it is going to be this one. So that's what we're going to do for all of those again. Now that we have the third nearest neighbors covered, let's move on to the 4th nearest neighbors, which are those yellow dots. Again, since this is a diagonal, the bisecting line is going to be a diagonal as well. So we're going to construct those for all 4 of the yellow dots. And the very last part of step 4 will be constructing the bisectors for the 5th nearest neighbors, so these dark green dots. They have a distance to the origin of 6 of those paper grid squares, so the perpendicular line will cross at half of its length, so 3 squares, which means we're going to have one right here, and for the lower one, right here. So this is what our construction process looks like after step 4. We have our grid of lines, and the only thing left to do is defining the Brillouin zones the same way I explained with this oversimplified example right here. So imagine standing at the origin and trying to walk into all of those different directions. The only area we can reach without crossing any lines, or by crossing 0 lines to use the official definition, is this rectangle in the middle right here. If your intuition now tells you, well, isn't that just the Wigner-Seitz cell? Your intuition is absolutely correct, because that's not a coincidence. The first Brillouin zone is the Wigner-Seitz cell in reciprocal space. So the green area is our first Brillouin zone. Moving on to the second, we now have to look for the areas we can reach by crossing one line from the origin. Those are going to be this little triangle right here, the same on the other side, as well as this area and its respective counterpart further down. So the blue area is our second Brillouin zone. For many problems this is already enough, but I've seen some practice problems or assignments ask for the third Brillouin zone as well, so let's do that. For the third Brillouin zone we have to look for areas we can reach by crossing two lines, and only two lines, and those are these little triangles right here. Same on the other side, of course. As well as these little triangles. And this larger area, as well as its counterpart down here. So all of those yellow areas are the third Brillouin zone. And that's it. That's all you have to do to construct Brillouin zones. To quickly recap the process, we're going to start by setting up the reciprocal lattice of our given lattice. We're then going to choose a central atom as our origin. For step 3, we're going to mark the nearest, second nearest, third nearest, blah 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 neighbors. For step 4, we're going to draw perpendicular bisectors on all of the connections between the origin and the marked neighbors. And step 5 is only a matter of definition, where we imagine starting to walk into all of those different directions from the origin and thinking about what area we can reach by crossing how many lines. I really hope you found this video helpful. If yes, consider leaving a like or sending it to a fellow student who might benefit from it as well. If you have any feedback or future video ideas, please type it into the comments down below. I reply to all of them. Thank you so much for watching and see you in the next one.